Hello everyone, I am Aditya and this is our third lectures on the series of mathematical series part 1, and we are starting with basic definitions of distributive proportion and variation. And as we know that I have written there in the introduction that this lecture introduces the basic concepts of ratios ratios, proportion, and variations. And we shall continue our discussion um, of exponentiations and logarithm over field hour. Finally, we shall define algebraic expression and study their basic types. So, as from clear understanding, I have decided to divide in three parts. So, we will we will first study ratio proportional variation, and then we move to our basic definitions of exponentiation and logarithm and their extension to our real number. So now begin with ratio proportion and variations. So ratio, when comparing two quantities, there are two common methods of comparison. The first method compares the difference between the quantities, while the second compares one quantities as a multiple or fraction of the others. So when we compare two such things, so when we do that thing, we often use in the terms of how much one quantities to the others, and another is that what multiples one quantities of other, like when you have to calculate the loss of expenditure when we buy something, we will actually do subtraction there. So at that point we will compare that things by subtracting one thing from another. And when we will have to see the variation, like um, as we do in percentage, all these things we use the multiple or fraction of other thing. The second method of comparison gives rise to the notion of ratio, or we can say the ratio compares one quantity with another by means of division. The ratio of two quantities A and B is denoted by A is to B and is numerically represented by A by B, and provided B does not equal to 0. These quantities A and B are called terms of the ratio. The first term is called the antecedent, while the second term is called consequent. Now move to another section, that is proportion. So what is proportion? A proportion means equality between two ratios. More formally, we can say that two ratios are equal when four quantities composing them are said to be in proportion. So A by B is equal to C by D. That is equivalent to writing that A is A is to B proportion to C is to D. Here A and D are known as streams and B and C are known as means of the proportions. So by multiplying both sides of BD, it gives AD is equal to BC. So that means the product of extremes equals to the product of means. So now move to the continued proportion. When when you see continued fractions, I mean when you see like fractions like that, A by B is equal to B by C is equal to C by D, then A, B, C, D are in continued proportion. This is just a definition. So now move to variation. A quantity A is said to vary directly as another when two quantities depends on each other in such a manner that A changed in same rate. So variation is something that showing the changes, how one quantity vary with another. So there are actually two types of variation. The first is direct variation. If two quantities are related with each other in such that an increase or decrease in first quantities result in corresponding proportionate in increase or decrease in second quantities. So when you have to when we do the normal calculation of time and distance, we have to measure that how much we measure that distance vary with time, where when the speed is fixed, or vice versa as p when time is fixed. I don't think that this happens, mm, but we can do some hypothetical scenarios. There are another examples too, like when we deal with percentage, like I have 5 percentage, there are 10 boys in coming the group of 5 percentage, how many boys coming in the group of 200%, like that. So that means that the initial increase in one quantities is vary with another quantities. So that is direct variation. In direct variation, if two quantities are related with each other such that increase or decrease in first quantities result in corresponding proportionate decrease or an increase in the second quantity, then two quantities are said to vary inversely with each other for some constant time. Yeah, see that thing. A is proportionate to 1 by v. That simply means there A is equals to m times 1 by b there for some constant m, and we can write like this: ab is equal to m. Joint variation, when change in one quantity depends on change in two or more quantities, it's said to be vary jointly with those quantities. So joint variation is simply that when a change of one quantity depends on more than two quantities, we can say that two or more than two quantities, we say that this is in joint variation. Application we use in time and work, time and distance, pipe and systems, mixtures, alligation, and financial mathematics, like when we have to calculate something, hmm, in time and distance, and how how much water is filled during that period of time, and all these things. And when we study in financial mathematics also, partnership, or or you can say that, um, finding the interest or compound interest, like all these stuffs, we use this concept called ratio proportional variations. Now move to the next and important sections: exponents and logarithm. Exponents and its properties. As we saw in lecture 1, exponentiation over the natural number was defined as repeated multiplication of an element, that is, n belongs to natural number. So we can write that an is equal to applying multiplication n times. Yeah. So the expression is a to the power n is called a power, and the element a is called the base. The natural number n is called exponents or index of the power. I had I already explained that thing in the first lecture. The above definition is valid only when the exponent is a natural. Our aim in this section to extend the notion of exponentiation to arbitrary real exponent, that is to define a to the power x for every x belongs to or under suitable condition on a. From this, one law falls out immediately: it will be single thread guides every extension we make in this node. So we have proved this law too, the index law. Every time we define e to the power x for some kind of number x, so we have just state for integer, where we'll ask what value of ax takes, so that index law keeps working. This turns each extension from the arbitrary renew rule into only choice consistent with what we already believe. So we are generalizing our notion when we notion of exponentiation. You can't say generalizing because just we are just extending our definition. So zero and negative exponents. So what does it mean by zero exponent? We have already defined that thing. So from the index, law demands an times a naught is equal to this, which forces a naught is equals to 1, and we prove that thing here. I am using as a definition. Negative exponent, again by law of index. So I have written like this. So an times a to the power minus n is equals to a to the power n plus minus n is equals to, when we add n plus minus n you get 0, and we know that from the first definition 3.2, a to the power 0 is equal to 1, which forces a to the power minus n is equal to 1 by n. Watch pattern as we half repeatedly. 2 cube is 8, 2 square is equal to 4, 2 to the power 1 is equal to 2, 2 to the power 0 is 1, 2 to the power minus 1 is equal to half, 2 to the power minus 2 is equal to quarter. Nothing new was invented. Each step forces by the one before it. So we have already proved that too in lecture 1. So these are just intuition behind definitions. Rational, or we can say fractional exponents. So exponents 1 by q, what does 1 by q represent? What should 1 half 1 to the power half means? By index law, 1 to the power half times 1 to the power half is, on adding we get a. So 1 half means that number which when squared gives a. By definition is root a. More generally for a positive integer q, a to the power 1 by q is written like that, and we qth root of a, and since a to the power 1 by q to the whole power q is equals to a to the power q by q, that is equal to a to the power 1 is equal to a. So we have generalized our definition of exponents up to rational. More generally we can say that a to the power p by q, we can define like that, uh, qth root of a to the whole to the power p is equals to qth root of a to the power p. From this point we require a greater than 0. If a is less than 0, the expression minus 1 half has no real value. So no negative bases are excluded once fractional exponent enters in the picture. So negative bases are excluded once fractional exponents enter in the pictures. When we study functions on exponents, we will explicitly define our a to be non-negative. I mean the base. So now move to the irrational exponents. This is the one genuinely new idea. What could 2 to the power root 2 possibly means? Given that root 2 is not fractional at all, we can excuse root 2 between fraction we already understand. Some which we already know that. So we are excusing root 2 between 1.4 to 1.5. Root 2 value is 1.414. So we are just excusing that thing, as a quick check on the table on section 2 shows that a greater than 1 increases the exponent, increase the value of a to the power x. So the same equality carry after exponentiation. So we are on, then we can take the exponentiation on both sides. And every number in the inequalities like 2 1.4 or 2 1.415 is the rational exponent, which we already know how to compute in section 3. In section this, mm, computing the first pair bounds numerically. So we are just numerically computing all those steps, and then we are approximating our desired desired result. Irrational exponents: a greater than 0 and irrational number x. Choose the sequence of fraction r1 r2 r3 that gets closer to x. Then ax is defined as the number that values a to the power r1, a to the power r2, a to the power r3 squeeze in on. Remark 3.13. In one sentence, every number is limit of fractions, and a to the power x for irrational x is defined as the limit of a to the power r over approximation fraction r. Summary: we have just did that for positive repeated multiplication. 0 we have defined like that, forced by this definition, and then negative again forced by this law. Fraction again forced by same law of indices. Irrational squeeze between the rational exponents. At every single stage, the only guiding principle was preserving the law of index. So now move to the law of exponent. Law of exponents. Each law below directly from the index law. A to the power m times e to the power n is equal to a to the power m plus n. The definition built up in the subsection 3.1.1 to 3.1.3 state AB is greater than 0 and mn belongs to R. The we have product rule, so that's like that. Quotient rule, a to the m by a to the power n is equal to a to the m minus n. Justification, just yeah, these are too trivial to prove that. We will just use that definition to get that thing. Power of a power. When you have power, whole power, you just multiply that those powers. So like that. Product of powers. So powers are so exponents are distributed over product. Power of a quotient. So again it is distributed over quotient. Zero exponent, as we have defined. Negative exponent, these are the just coming from definitions. Every law in this consequence and the consequence of the product law, not independent rule to memorize. If you forget one, they derive it from this. Logarithm. Now move to logarithm. The logarithm is defined as the operation that undergoes exponentiation. It answers the question, to what power I raise to get x. Simply, these are inverse. These are equivalent to each other. Here you are dealing with finding the power power of the expression. Like you have 2 to the power q, 2 cube. You just calculate that thing and you get the answer. And now exponential logarithm asks the question that what we raise 2 on the base 2 to get 8. We have just discussed in lecture 1. The restriction a is not equal to 0 is necessary. 1 to the power y is equal to 1 for every y. So when we define function, we will use that thing. Special cases, these are called common logarithm, and when you have base e, this is called natural logarithm, lnx. Immediate consequences, so these are just consequences, or we can say properties of logarithm, and these two are symmetric to each other. Three main properties. So logarithm is when you have product, you get distribute in sum, like that, and this proves from this definitions. Oh, sorry, this results a to the power m times a to the power n equal to a to the power m plus n. Now quotient property, you have log xy to the base a, you get log x to the base a, log x to the base a minus log y to the base b. Power properties, when you have power, it jumps to the back on the first thing. So these things are too trivial to prove, just try it on. Now very important properties is the change of base. Log x to the power x to the base e is equals to log x to the base b log a to log a to the base b. So you have to just change that base, so you are just taking the base with base x, and then you have taking the base with a. And there is another consequence is base change. Okay, this is also the consequence of the upper property, that the base and the value, yeah, and B and A are interchanged. Now move to the algebraic expression. Definition: what is an algebraic expression? It is a combination of constant variables connected by algebraic operation of addition, subtraction, multiplication, division, and exponent by a rational number. Exponentiations by a rational number. It doesn't need to have rational because we have defined up to real, so it could be anything. So what is term? A single product con of constant variables occurring in algebraic expression. The terms are separated from one another by plus or minus sign. In 3x square plus 2xy minus 5, the terms are 3x square, 2xy, and minus 5. So now types of algebraic expression by number of terms. Monomial, you have one terms, so you can say that this is monomials, and the examples are 5x square 1 minus 7, 3xy. Binomial, you have when you have two terms. Trinomial, when you have three terms. Multinomial, when you have multiple terms. Polynomial, when you have multiple terms with non-negative integers. So now these move to algebraic operation. Four basic operations on algebraic expressions. So when you have to do algebra, so we will just combine like terms. Like terms means they have same variables as well as exponents. Like 3x square plus x square. These two are like terms, we combine them. 4x square minus 3x. Multiplication, you are just using distributive property over that, and you get the whole expression. The factors and division is cancelling of factors. Symmetric, cyclic, alternating, and anti-symmetric expression. These classifications describe how an expression in several variables behave when its variables are permuted, rearranged among themselves. An expression is called antisymmetric if it remains completely unchanged under every possible arrangement of its variables. So you have expression, you can change any with x with y, y with z, z with x, and you get same expression. That is called symmetric. Swapping of any two variables, rearranging all three in any order gives same expression. Likewise this. Now move to cyclic expression. An expression is called cyclic if it remains unchanged under cyclic shift. You are just shifting. Cyclic shift means um, x1 with x2, x2 with x3, x3 with x4, and like that, and the next one with again x2. But it is not required to stay unchanged under an arbitrary permutation. We can't apply any order of permutation. It should be cyclic. For example, this turn into this, which is the same expression recorded, however it is not symmetric. Swapping just x, y just give generally different expression. Every symmetric expression is automatically cyclic. Yeah, it is true, but cyclic expression need not to be symmetric, as the example above shows. Alternating or antisymmetric expression. An expression is called alternating or equivalently antisymmetric if swapping any two of its variable reverses its sign. So you are just changing any two variables and you get minus 1. in each factors. This is explained here. Under general permutation, sigma, not just single sweep, an alternating expression gets multiplied by plus 1 if sigma built from even number of swap, uh, and by minus 1 if sigma built from odd number of swaps. So is called sign of permutation. This a consequence of worth noticing: if an alternating expression has two variables equal, swapping those variables changes nothing on the left side but forces minus f on the right, so f is equal to 0. This is why every alternating expression contains a factor like xi minus xj for each pair of variables, exactly what you see in x minus y minus z, z minus x in this term. So that's all for today. We will meet in the next lecture of this series. So thank you. Have a nice day.